Good afternoon, everyone. My name is Deepak. I work at IBM at their India office. I've mostly worked with BMC firmware development teams. Over the last few years, I've been focused on OpenBMC, which is an open source BMC firmware stack implementation. And I'm here today to talk about PLDM. So how many of you know about PLDM? Okay, that's a good number, so that makes my job easy, I guess. So let's get started. So before I speak about PLDM, my talk is actually kind of structured into two parts. Before I speak about PLDM, I'd first like to provide an overview of something called PMCI. PMCI stands for Platform Management Component Intercommunications. It's a group associated with DMTF, and that group's goal is to define standards for inside the box communication protocols, inside the box or in band. So PMCI is basically a family of protocols. And PLDM, which stands for Platform Level Data Model, is one of them. So on this picture, you actually see four kind of components, and PMCI deals with intercommunications between these four components. There's, of course, the BMC at the center. There's also the platform software on the top, which is basically firmware running on the host CPU. Typically talks to the BMC using physical interfaces like KCS or serial-based interfaces, and the platform firmware talks to the BMC to accomplish some kind of management functions. There are managed devices which are typically connected to the BMC or SM bus or PCIe, and those devices respond to management-based requests from the BMC. The BMC can actually talk to other kinds of BMCs. For example, if you have a system design where one BMC acts as the out-of-band interface provider, and the other BMC deals with inside the box communications. Then there's also a remote management console. The interface there to the BMC is actually not in band; it's typically over the network. But the remote management console can issue something like redfish to the BMC, and then the BMC transforms that to an in-band communication path to talk to other devices that are connected to the BMC. So these are broadly the four kind of components that PMCI deals with. On this picture, you also see four communication paths. I think I spoke about some of them. So that's basically the BMC and the host, BMC talking to a BMC, BMC talking to a managed device, which can also be an NC, a network controller. And PMCI has defined four protocols to kind of tackle these communication paths. At the very core is something called MCTP, the Management Component Transmission Protocol. MCTP is the goal of MCTP is to abstract how messages are sent inside the box, to abstract out the details of the physical medium. How this is achieved is PMCI defines an MCTP base specification, but also defines a family of binding specifications that help you map MCTP to physical buses like SM bus or PCIe, etc. There are also a family of binding specifications that run on top of MCTP, and these let you transport protocols, payloads like PLDM and NVMe MI over MCTP. So that's MCTP. The next protocol, of course, is PLDM. PLDM is a way to abstract hardware management functions, things like temperature, monitoring temperatures, fan speeds, through inventory, the typical management functions. PLDM abstracts them and provides an efficient way to exchange those management information between inside the box between different management components. There are two other protocols. There's a protocol called SPDM, Security Protocol Data Model, which deals with, again, inside the box device authentication and firmware management. And lastly, there's NCSI, which basically talks about how the BMC can talk to the network controller. So this picture just groups different layers in the PMCI stack. At the very bottom is the physical layer, and currently all of the PMCI protocols are defined to function on these physical layers, but more can be added here if there's a need. So SMBus, KCS, PCI, vendor defined messages, the serial interface, and RMII. There are two transport protocols. There's MCTP that I spoke about with the bindings that are shown here. And there's also RBT, which is RMII-based transport. At the upper layer are the data model protocols. There's PLDM, which we'll look at today. But there's also NVMe, MI, NCSI, and there's an MCTP control specification that's defined. Okay, so PLDM, again, is actually a family of specifications. Each specification defines basically a type code for a specific set of commands that belong to that PLDM family. And I can quickly go through the different specifications to kind of talk about what's provided in each spec. There's the PLDM base specification, which defines the common message fields based on which the other PLDM specifications are defined. There's a binding specification that lets you transport PLDM payloads over MCTP. There is a PLDM ID and code specification, which just defines IDs for each of these specs that you look at here. Then there's a PLDM state set specification. Similar to IPMI, PLDM has the concept of entities. And the PLDM state set specification defines a set of enumerations for common states, such as the health of an entity, or the power state of an entity, or the availability of an entity. And the state set specification defines common enumeration values that can be used for these state sets, and then those can be associated to an entity. Then there's a specification for exchanging through data information between components using PLDM. There's PLDM specifications specifically for SMBIOS-based transfers. There's a PLDM for BIOS control, which defines data models and commands that lets a BIOS talk to a BMC. The PLDM platform monitoring and control specification deals with things like modeling sensors, commands related to transferring sensor-based information between management components. A couple of recent specifications, the PLDM for firmware updates, that defines commands for in-band firmware updates, and Redfish device enablement, which is a fairly recent spec as well, that lets PLDM devices participate in Redfish-based out-of-band management. Okay, so this slide is about basically some of the motivation to start implementing a PLDM stack on OpenBMC. So some of this are kind of specific to what we started noticing on IBM systems, specifically enterprise class systems. So we had instances of the host firmware talking to the BMC using in-band IPMI. And one issue that we came across was because you can have up to only 255 sensors in IPMI. That was a problem when you have to kind of scale to larger systems. And then you could do something like OEM IPMI, defining 2-byte sensors, but again, that's not standard. Okay, so PLDM defines sensors that are 2 bytes long. So that kind of deals with the problem of having a limitation with just 255 sensors. PLDM also introduces the concept of effectors, which are basically a control mechanism. So I've seen IPMI stacks where sensors are used as control mechanism, whereas sensors are typically supposed to be read-only data. So effectors is a way to change, for example, the power state of the system. So those kind of functions can be achieved via PLDM effectors. With the PLDM stack, a device implementing a PLDM stack can be a requester or a responder. So a requester is like a PLDM client, and a responder is a PLDM server. So with this, you could have two-way communications between the host firmware and the BMC. So these were some of the points that was basically from the motivation to start implementing a PLDM stack on OpenBMC. I have a link out there which has more details about the about motivation and in general the design of the PLDM stack on OpenBMC. Okay, so this is the next slide. We look at some of the components that form the PLDM stack on OpenBMC. Actually have a slide for each of these, so let's look at that. Okay, so the PLDM stack on OpenBMC has a library called libpldm. This is a C library, and the primary purpose of this library is to define data structures that help in serializing and deserializing PLDM messages. It's a C library, and it lets you do things like encode a PLDM message and both request and response messages, and it also has APIs for decoding incoming PLDM request messages or decoding incoming responses. This library is intended to be platform independent. What I mean by that is it does not have any OpenBMC dependencies. So that way, other firmware stacks, for example, host firmware stacks, can make use of this specific component of PLDM. There's another library which typically which implements functions that that kind of help the BMC to act as a PLDM responder. So this is implemented in modern C++, and it makes use of OpenBMC APIs because this library is specific to OpenBMC. So if the BMC has an incoming PLDM request message that is to read a certain temperature, then this library would have a handler that maps the PLDM sensor-based constructs to how sensors are natively implemented in OpenBMC. Which could be something on the D-bus or a sysfs entry, for example. So this library has the handlers for transforming PLDM constructs to OpenBMC constructs and to form response messages and send them back to the requester. Also, several PLDM constructs, for example, the BIOS tables or the fru inventory, the responses there are very system specific. That's why we make use of config files, which are mostly written in JSON, where you could feed in config information that's specific to your system or platform, and the libpldm responder prepares response packets based on these config files. Okay. So PLDM, like we saw on the PMCI stack, PLDM runs on top of MCTP. So the third component in the PLDM stack is a PLDM daemon. So this daemon makes use of of libmctp, which is basically an MCTP implementation that exists today on OpenBMC. The PLDM daemon links with libmctp, and it helps in receiving PLDM request messages to the BMC, and also to send out PLDM messages to other MCTP devices that are connected to the BMC. There's also a PLDM tool that we've written. This is basically a PLDM requester tool. This runs on the BMC. It again, and it can talk to the PLDM daemon using libmctp. There's actually going to be a session about this tomorrow, so we'll look at more details about the PLDM tool. PLDM, the PLDM specifications let you define OEM commands as well as extensions, OEM extensions to standard commands. The way we deal with that is you can have an OEM section that is conditionally built in with the base PLDM stack, and that OEM implementation can have their own response handlers and their own libPLDM extensions to encode or decode the OEM commands or OEM extensions. Okay, so we've just started with the PLDM stack implementation on OpenBMC, so there's not a lot of commands that are kind of implemented and supported yet, but the libPLDM library, these are the kind of set of commands that are implemented today. From the PLDM base specification, there are a bunch of commands that form something called as the PLDM discovery. So things like getting the version of the PLDM implementation, getting a list of supported commands. So those basic set of commands are implemented. There are some commands implemented from the PLDM BIOS specification that lets the BIOS firmware, for example, store BIOS tables on the BMC, and then the BMC can expose those to remote consoles using Redfish, for example. And there are also some commands implemented in from the monitoring and control spec. There's the get PDR. PDR stands for platform descriptor record, similar to the IPMI sensor data record. That provides you semantic information about different sensors and effectors that are present on a system, based on which further sensor-based commands can be sent out to the BMC. So that specific command is implemented. Okay, so this is a flow diagram or a sequence diagram of the BMC acting as the PLDM responder. So what you typically have is a PLDM requester, which could be the host firmware or another BMC that sends our PLDM request message over MCTP. That's received by the PLDM daemon. The first thing that the PLDM daemon needs to do is basically decode the incoming request into the different request parameters. That's done via libPLDM. And after that, the PLDM daemon, because now it knows about the specific PLDM command that it has to serve, it can send that information to a libPLDM responder, where a handler specific to a PLDM type and command will be invoked. The handler makes use of OpenBMC APIs to come up with a response, and then again uses libPLDM to encode the response as PLDM. And finally, the encoded response is sent back to the requester over MCTP. Yeah.
How do you transport, what is before that? What is shift left? Is it using KCS ports? Is it still using KCS ports? Or is it...
Yeah, that's a good question. So if you're specifically talking about the host BMC interface, so that could be KCS, that could be serial, or that could be something like LPC. So the good thing about MCTP is it abstracts that to the PLDM layer. So the PLDM is still dealing with MCTP APIs, standard MCTP APIs, but you could have bindings, MCTP bindings that are plugged in, which are relevant to your system, or rather relevant to the interconnect between the two devices.
But at the same time, as you said, it works as a request and responder both, right?
Right.
So then KCS and SMBIOS has to have that support, or like a I2C slave to be supported at the bottom layer.
Yeah.
Do you expect that?
So, I mean, honestly, I don't know about use cases with KCS. So I can tell you that at least on some of the IBM OpenPower hardware, we have the host talking to the BMC using PLDM or an LPC interface. There isn't an MCTP or LPC binding that exists today. That's something that we'd have to write. So, I mean, the limitations of the underlying physical buses that you're speaking about, I think they still exist. So MCTP or PLDM, those specifications don't really solve that.
Yeah, but when you say that MCTP over LPC, I assume it's KCS, right?
There is an MCTP over KCS standard binding already that exists today. There isn't an MCTP or LPC binding that exists today.
And it does work both the way, request and respond.
I don't think that's too bidirectional. I mean, that limitation is based on the physical bus. So, I mean, there isn't anything in MCTP or PLDM that precludes two-way communication. But the physical medium could do that, if that's what you mean.
So if BMC want to be a PLDM request, can it use the lib PLDM? You know, the most common case is BMC talk to the option device.
Yes.
Right. But in this case, the BMC, the responder, actually hosted is using PLDM to access the BMC, right?
Right. So, yeah, I mean, libPLDM itself has APIs that serve both the requester and responder flows. So, so to answer your question, yeah, I mean, if the BMC is acting as the requester, then the specific BMC application that is implementing a certain requester functionality can make use of libPLDM to encode outgoing requests. I actually have a slide on the requester flow as well. We'll look at that. Okay.
Sorry.
Yeah.
So coming back to the physical limitation. So basically, MCTP requires multi-master support in I2C if we are implementing our SMBus I2C. Would it be, I mean, if you are using LPC in your systems, is there bidirectional support in the hardware? Or?
I think it's probably makes use of KCS interrupts to kind of enable that.
Okay, one other question as well. So if we want to implement it on the host side, the only part in this implementation, the libPLDM responder is kind of tied to OpenBMC stack.
Right.
Rest of them can be ported as is.
Yeah, that's correct.
Okay.
Because it's typically only the responder that has to be platform aware to serve incoming requests, right? I think we looked at this already. These are some of the commands that have been implemented today for the BMC acting as the PLDM responder flow. So this is the sequence diagram where the BMC is actually acting as a requester. In this case, I don't think that there would be actually a do-it-all PLDM daemon which acts as a requester, because the requester functions, the way we envision it, would be actually separated into different applications that are dealing with specific functionalities. For example, there could be a BMC requester app that's doing firmware updates for a connected device. So that would be a different application. So in this sequence, again, the requester app makes use of libPLDM to encode the request and form a PLDM request message. Each PLDM request message has to have a unique instance ID that basically helps route request messages and deal with incoming response messages, because you could have requests sent out concurrently, and you're not supposed to expect a response that kind of comes in the same order. So the requester app can get the next unique instance ID via some kind of IPC with the PLDM daemon. And once that's done, the requester application, again over MCTP, sends out the PLDM request message to the responder, which, for example, could be a device that's connected over SMBus or PCI. The device serves the PLDM request message and sends back a PLDM response, which again has to be decoded, and the requester app can then deal with the actual payload in the response message. Okay, so this one is quickly about how to get involved in the in terms of contributing to the PLDM stack on OpenBMC. So similar to how it is with other OpenBMC applications, patches are always submitted to the OpenBMC Gerrit for review. So you can, for example, watch out for, looking at the OpenBMC Gerrit for the PLDM project kind of tells you about the current work that's happening out there. The PLDM stack code on OpenBMC is on the OpenBMC GitHub. So looking at the issues there or writing issues there for problems faced with the PLDM stack is a good way to get involved as well. And there's also the OpenBMC mailing list and IRC information here where people can answer PLDM questions. Some of the references. So my initial couple of slides about the PMCI stack, you can find more details about that in the PMCI white paper. I have a link for that. And all of the specs that I spoke about, the PLDM specifications, the MCTP specifications, and the binding specs, they're all, there's a link where all of them are kind of uploaded as well. So I think this was my last slide. Thanks for attending, and I can take more questions at this point of time.
Yeah, I'm curious, is there any thought put into security or authentication over requests, for requests over PLDM?
The way I've understood that is, I don't see like security being built into the PLDM protocol or specs themselves, but I believe PLDM has to work in conjunction with the SPDM protocol, security protocol data model. So that protocol deals with some of the things that you just asked about, like authentication and firmware measurement. Any other questions?
What's the real benefit? I'm still not very sure. It's like my replacement.
Not really. I mean, there are like problems with IPMI. The sensors was one that I spoke about, and I think IPMI also lacks control mechanisms. So PLDM effectors is like an effective way for controlling states, for example, and I believe there, even with the transport interfaces of that IPMI spec defines, block transfer is one of them. I think there are benefits that you would see that actually becomes a block transfer versus MCTP comparison. So there are benefits in those areas as well, because MCTP kind of abstracts you from the physical mediums, and there are more physical mediums supported as in general compared to IPMI.
When the BMC is acting as a requester, what sort of other devices do you anticipate providing PLDM interface with the BMC to be talking to?
So I guess some kind of IO adapters, for example, which need temperatures to be monitored on that device for for I don't know, bumping up the fan speeds, for example. So yeah, the BMC could be managing temperatures on that card using PLDM.
Do you see, is there much hardware that exists today?
That's a really good question. I mean, I believe there is adoption. So I know for example, for some of the vendors that IBM systems deal with, they are coming up with cards that support the PLDM stack.
So, do you also support the channeling? Because if multiple requests and multiple response coming all the way together, so how do you differentiate, or do you have channel informations in the package?
By channel, you mean, are you talking about IPMI based channeling or?
Similarity, like in PLDM, how do you deal? Like in IPMI, we deal with the channel numbers and respond and connect with the interface. But how do you deal in PLDM?
So, I mean, the PLDM specs, the PLDM base specification does talk about how multiple requests can be sent out, and using using combinations of the transport ID. So MCTP has something called an EID, which helps you identify an endpoint, which is the origin of the message. So using a combination of that and the PLDM instance ID, a responder, for example, can distinguish PLDM request messages that are coming from different devices.
So you mean to say that MCTP handles this channeling thing?
MCTP handles it, and PLDM, the PLDM layer handles it to the level of the instance ID. So So yeah, there are actually 3 IDs. There's the PLDM terminus ID, the MCTP ID, and the instance ID. So a combination of these 3 let you deal with concurrent messages coming from different devices. Any other questions?
Since PLDM is a DMTF spec, any thought on hosting libPLDM there?
So we've discussed this with PMCI. So they're not really interested in a reference PLDM implementation, but they're definitely interested in a PLDM tool, kind of similar to Redfish validator tool. So if we write a PLDM tool with validation capabilities, I'm pretty certain DMTF will be interested in hosting that.
Is OpenBMC the first to implement PLDM?
Yeah, that's what the DMTF folks tell us.
Okay.
Or rather, not the first, but the first open source implementation of PLDM. All right, thanks everyone.